Centuries into the voyage, a pump begins losing pressure. There is no explosion and no emergency through the ship. A technician finds the fault, checks the maintenance history, and retrieves the replacement part that earlier generations expected would eventually be needed. At first, this seems like exactly the kind of failure a generation ship should be prepared for. The old pump comes out, the new one goes in, the line is tested, and the system returns to service. But replacing the pump is only possible because many other things are still working. The crew needs tools that remain accurate after centuries of use, seals and materials that have not degraded, and a workshop capable of making parts that were never stored in the first place. That workshop depends on power, cutting equipment, measurement tools, software, and people who understand not just how to replace a component, but why it failed and whether the replacement will solve the problem. And over a voyage lasting hundreds or thousands of years, none of those supporting systems can be assumed to last forever either. A generation ship cannot simply carry a spare copy of everything that might eventually break. Even if there were enough storage space, spare parts would age, some materials would deteriorate, and the machines used to repair other machines would themselves need maintenance. A large inventory might buy time, but eventually the ship has to be able to manufacture, recover, and rebuild what it needs. That changes the problem completely. The question is no longer whether the crew can repair one failed pump. It is whether the ship can preserve the entire chain that makes repair possible. The ability to produce useful materials, keep precision equipment working, recycle worn components, and pass technical knowledge to people born centuries after the original engineers are gone. A repair that looks simple today could become impossible much later, not because the failed part is especially complicated, but because one of the systems behind it has slowly disappeared. The tools may no longer be accurate enough, recycled material may no longer meet the required standard, or the knowledge needed to diagnose an old design may have been lost. That kind of decline does not have to arrive as a dramatic failure. It can happen gradually, while most of the ship continues to appear healthy. So surviving for centuries would require far more than durable machinery and generous stocks of spare parts. A generation ship would need to preserve enough industry, technical knowledge, and material recovery to keep rebuilding the systems that keep everyone alive. By the end of this video, you will understand what true self-repair would require on a generation ship, why spare parts alone are not enough, and how a civilization could gradually lose the ability to maintain itself long before the ship itself stops working. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. If the failed pump is only a symptom, what gives way first? The hardware itself, or the shrinking margins and support loops beneath it? A ship can survive a broken pump. The crew finds the fault, shuts down the line, and brings another pump into service while the damaged one is repaired. Engineers can plan for that kind of failure. It has a name, a location, and a person assigned to fix it. The harder problem begins when nothing has failed badly enough to demand everyone's attention. A seal leaks a little more than it did last month. Dust gathers inside a fan housing. A sensor gives a reading that is probably correct, though nobody fully trusts it. Somewhere else, a hinge stiffens, a cable sleeve cracks, and corrosion grows beneath a panel that is rarely opened. You could manage any one of those jobs. The trouble is that they don't arrive one at a time. Several may appear during the same week, while yesterday's repairs are still unfinished and new inspections keep finding more work. On Earth, maintenance can reach beyond the building where the trouble appears. A technician can call a manufacturer, order a tool, consult the engineer who designed the system, or bring in another team. A centuries-long ship has only the people aboard, carrying knowledge that must survive every retirement, birth, disagreement, and imperfect lesson. That changes the work. The crew isn't simply repairing machines. They're deciding which signs deserve attention now, which can wait, and which harmless-looking fault might be connected to something worse. Every inspection takes time away from another inspection. Every difficult repair may need the same skilled hands already working elsewhere. The danger is backlog. It grows slowly because most of its parts don't look dangerous by themselves. A light remains dim for weeks. A door takes 2 attempts to close. A filter is replaced later than planned because the medical bay needs help. Most of these events never become a crisis, yet the unfinished work keeps collecting. Eventually, the crew begins living with small defects. They learn which display flickers, which valve sticks in cold conditions, and which alarm can be cleared after checking a second sensor. Familiarity makes daily life easier, but it also makes decline harder to see. We're good at getting used to problems when they arrive gradually. A ship can become less reliable without any single day feeling much worse than the day before, and no warning light announces that the balance has started to tip. After decades, maintenance is no longer a series of separate repairs. It becomes a competition for attention across thousands of aging parts, limited working hours, and knowledge that isn't shared evenly. The decisive loss may not be an engine or an air processor. It may come when faults begin appearing faster than people can understand and clear them. So how could a crew keep that burden from growing across generations, when even the people deciding what to repair will keep changing? The International Space Station gives us a small, close-to-home version of that burden. It has been continuously occupied since November of 2000, yet it has never simply settled into working. Crews spend much of their time inspecting equipment, cleaning filters, replacing worn components, tracing leaks, and fixing the machines that support their work. Endurance on the station is an activity, not a condition. NASA and its partners designed the station for repair, and Earth remains close enough to help. Engineers on the ground can study a fault, send instructions, prepare replacement hardware, and place that hardware aboard a cargo flight. Even with all of that support, maintenance shapes daily life. The station survives because people keep noticing small changes and acting before those changes become larger ones. It also survives by accepting decline. Solar arrays produce less power as they age. Micrometeoroid strikes leave damage. Seals, pumps, computers, and cooling equipment don't all remain at their original performance. Some parts are replaced, some are patched, and some losses are worked around. The aim isn't to return the station to the exact state it had on launch day. The aim is to keep the whole system safe enough to use. Voyager shows the same pattern over a much longer stretch, far beyond the reach of a repair crew. Voyager 1 and Voyager 2 launched in 1977. Their radioisotope power sources have weakened every year since then, so engineers have gradually switched off heaters and instruments to preserve power for the remaining work. The spacecraft haven't stayed unchanged. They've been managed through a long, planned narrowing of what they can do. In 2023, Voyager 1 began sending back unreadable engineering data. The spacecraft was still receiving commands, but part of its flight data system had failed. Engineers at NASA's Jet Propulsion Laboratory spent months reconstructing how software written decades earlier was arranged inside a machine more than 20 billion kilometers away, over 12 billion miles, where a command takes nearly a full day to arrive. They found a way to move the affected code into other parts of memory, dividing it because no single open region was large enough. Voyager 1 resumed returning usable engineering information in 2024. It was a remarkable recovery, though not a return to youth. The damaged hardware remained damaged, power kept falling, and every successful adjustment had to respect limits that could no longer be removed. That is what graceful decline looks like. A long-lived machine continues because its operators understand which abilities must be protected, which can be reduced, and which may have to be surrendered. Success is not perfect restoration. It is preserving enough function with enough understanding to keep going. The station has crews, cargo flights, and thousands of specialists on Earth. Voyager has a small team reaching across hours of radio delay to software from another era. A generation ship would have neither form of support, and its maintenance choices would shape lives not yet born. So who would decide what the ship could safely give up? On a generation ship, the first warning might not be a major failure. It might be a growing list. A seal in one farm needs inspection. A temperature sensor gives readings that no longer agree with its neighbor. 2 cabin fans are making the same faint rattle, while a third has already been removed for repair. None of these problems threatens the ship tonight. Each can wait a little while, and that is exactly how the danger begins. Every repair creates several kinds of work. Someone has to notice the fault, find its cause, decide how urgent it is, gather the right parts, carry out the repair, and then prove that the system is safe again. If the replacement changes how another system behaves, that must be checked as well. Closing one job can open 2 more. For years, the crew may stay ahead. New faults appear. People clear them, and the list remains manageable. Then the balance starts to shift. Older equipment may take longer to inspect. Earlier repairs may leave less room to reach a cable or valve. A rare skill may now belong to one tired person who is also training someone younger. The work has not become impossible. It has become slower. You might not notice that change at first. If you lived aboard, your cabin would still have light and moving air. A breakfast would still come from the farms. The repair teams would look busy, perhaps busier than ever. From the outside, the ship could seem healthy because most things would still work. Yet once faults arrive faster than the crew can diagnose, schedule, repair, replace, and verify them, unfinished work begins to accumulate. The ship is no longer dealing with separate defects. It is carrying a backlog, and every day that backlog makes tomorrow's work harder for everyone aboard. Backlogs change decisions. A weak pump that once would have been replaced this week is moved to next month because a cooling fault needs attention first. Its vibration then damages a mounting bracket, which adds another job. Meanwhile, the postponed inspection of a power cable means its insulation keeps aging unseen. The crew can work harder while the ship falls further behind. This is maintenance drift, a widening gap between what the ship needs and what its people can finish. It can be difficult to see from inside because many systems still run. More of that continued operation now depends on temporary fixes, delayed checks, and equipment being pushed closer to its limits. The queue starts shaping the ship before anyone has chosen what to surrender. A ship can endure damaged machinery. What it cannot endure forever is losing control of the queue itself. When the crew no longer knows which delayed task will combine with another, graceful decline becomes harder to direct. Sacrifices stop being chosen and begin arriving through failures. And if the maintenance list keeps growing across generations, who gets trained, trusted, and given the authority to decide which work must come first? Redundancy is how the crew buys time. If one cooling pump stops, another can carry the load while the first is opened, cleaned, and repaired. If a control board burns out, a spare can slide into its place. The failure still happened, but it did not become an emergency. That protection is real. On a ship where every machine supports human life, parallel equipment turns many sudden breakdowns into scheduled work. The lights stay on while someone replaces a bearing. Air keeps moving while a damaged motor is rebuilt. A bad circuit board becomes a job for Tuesday morning, rather than the reason everyone wakes up at once. Engineers can extend that protection by keeping several layers of backup. There may be 2 working pumps, a third held ready, spare bearings in storage, and replacement boards sealed against moisture and dust. Some parts can even be moved between systems if they share the same fittings and electrical connections. Each choice gives the crew another way around a failure. For years, this can work extremely well. One pump fails, then returns to service. A board is replaced, tested, and kept as a repair candidate. Bearings leave storage slowly enough that the shelves still look full. From inside the ship, redundancy can feel less like a temporary defense and more like proof that the design is lasting. You can see why that feels reassuring. That impression deserves respect because the backups are doing exactly what they were built to do. They absorb bad luck, protect repair time, and stop one broken part from dragging several systems down with it. Without them, the first decades would be far more dangerous. Still, every backup belongs to an inventory. The spare pump has seals that age. The stored board has components that may fail when powered after years in darkness. Bearings can be preserved, inspected, and rationed, but every bearing placed into a machine leaves one fewer on the shelf. Even parallel systems gather hours of wear while they wait for their turn to carry the load. The crew can repair some parts and rebuild others, which stretches the inventory far beyond a simple count of boxes. A worn shaft may be machined again. Copper can be recovered from a dead motor. 2 damaged boards may provide enough working pieces for 1 good board. This is skilled maintenance, and for a long time it keeps scarcity from looking like scarcity. Yet the frame remains finite. Redundancy does not erase failure. It spreads failure across more equipment and more years. It changes a single broken pump into time for repair, then changes a shelf of spares into decades of choices. As the voyage continues, protection depends less on whether a backup exists and more on how many times the crew can restore what has already been used. A spare part looks like an answer until someone installs it. Then the shelf holds 1 fewer answer, while the machine may fail again for the same reason. If a ship carries 20 replacement valves, that doesn't mean it has protected 20 valves forever. It means the crew can make 20 valve replacements across every system that uses that model. After the 20th replacement, the promise ends, and because several machines may depend on that same valve, no one can reserve the count for a single system. The count becomes awkward because failures never divide themselves evenly. One valve may last 80 years, while another faces heat, vibration, or corrosive chemicals and fails every 12. A warehouse planned around the average can look generous on launch day, then empty one particular bin while nearby shelves remain full. The ship may still possess thousands of parts, just not the small seal required to keep a vital line from leaking. Repeat use changes the meaning of every number. Suppose 12 air handling units share the same bearing, and the ship carries 60 replacements. At first, that sounds like 5 complete rounds of protection, yet the units won't fail together, and some locations will consume bearings faster than others. A rough unit might use 8 before a sheltered one needs its second. Those 60 bearings aren't 60 equal years of safety. They're a shared allowance being spent at different rates. You can see why a stock list alone tells the crew so little. They need the rate of use, the difference between the easiest and harshest locations, and the chance that several failures arrive close together. A part lasting twice as long does more than add comfort. It slows the subtraction. A design change that lets one bearing fit 4 machines can also combine separate reserves into one larger pool, although every machine then draws from that same supply. Flexibility helps, but it also joins risks that were once separate. There is another catch. Replacing a failed part can make the machine work again, but it doesn't restore the inventory. The new bearing on the shaft is no longer a spare. The empty space in its crate stays empty unless the crew can manufacture another one with the required size, material, and finish. Until then, the repair has exchanged stored capacity for more operating time. Nothing on the shelf has grown back. This makes the warehouse less like permanent protection and more like a set of clocks, each counting down at an uneven pace. Some may barely move for a century. Others may lose years during one bad season. Crews can slow those clocks by sharing designs, recovering components, and deciding which machines receive the best remaining parts. They can revise forecasts as real failures replace estimates with experience. They still cannot make a stocked replacement renew itself. Every installation is a subtraction, and every subtraction leaves a smaller buffer for the failures still ahead. A ship can own 500 spare valves and still be unable to make one. Full shelves hide that difference. Using a finished part is simple because the difficult work was completed in factories on Earth, perhaps centuries earlier. Making the next valve aboard is much harder. The crew needs a suitable material and a machine that can shape it. Then they must measure the result and prove that it will survive years of use. All of this depends on equipment that also wears out and must be maintained. A warehouse, then, is stored work. Mining, refining, design, manufacturing, testing, and transport were all completed before launch and packed into finished shapes. It is also stored judgment. because each finished object carries thousands of choices about tolerances, treatments, assembly, and quality control. The crew inherits the results without inheriting every factory that produced them. Once an item is installed, the ship has consumed a small piece of that inheritance. A capable workshop can make it last much longer. Metal from a retired pump might become a bracket. A worn gear could be measured, redesigned, and cut again. Three-dimensional printing may produce some shapes with less waste, while computer-controlled tools can repeat designs with great precision. If you've ever fixed one machine by taking apart another, you already know the basic trade. The workshop can recover value from what the ship still has, but it cannot create material from nothing or repair every component inside itself. Suppose the printer fails because a sensor has drifted. Its replacement may require a clean room, a silicon wafer, special chemicals, and manufacturing equipment far more complex than the printer it serves. Carrying another sensor postpones the problem. Carrying a machine that makes sensors moves the problem deeper, because that machine also contains parts that age. The crew, therefore, faces a chain of dependence. Remaking the ship requires usable material and working tools, plus the ability to maintain those tools. Lose one small link and everything beyond it may become unreachable, even when the plans are clear. No ship could carry a complete copy of Earth's industrial base. Its designers would have to choose what the crew could reproduce and what stored supplies would cover. That choice costs the mission before anything breaks, because every workshop machine consumes limited resources and skilled attention. Over time, the crew would need help tracing these links, watching thousands of machines and deciding what to make before a shortage became fatal. We may be able to build machines that carry much of that burden across generations. Once the stockpiles are no longer enough, how much of the ship's repair work could robots truly take over? A repair robot could give a generation ship something close to an extra pair of hands that never retires. It might inspect pumps while the crew sleeps, carry heavy parts through narrow service spaces, or repeat the same careful weld hundreds of times. With enough machines working together, a small crew could maintain far more equipment than human labor alone would allow. That sounds like multiplication, and in one sense it is. A robot can copy a practiced action across many hours and many locations. If one machine maps a hairline crack, others can search for the same pattern elsewhere. If a repair method improves, the new instructions can spread through the fleet without waiting for every technician to learn the task separately. Yet the robots belong to the ship's maintenance problem too. Their joints wear down, cameras collect dust, force sensors drift, cutting tools lose their edge, and batteries slowly hold less charge. A machine that places a seal with perfect pressure today may press too softly years later unless someone checks its calibration. You can see the catch. Each new pair of hands also adds another machine the ship must keep healthy. The ship gains workers, but it also gains more workers that need care. Some of that care could be done by other robots. One machine might test another, replace a damaged motor, or compare its measurements against a fixed reference. This would reduce the number of human hours needed for routine work. It wouldn't make the fleet independent, because the test equipment can drift as well, and a robot cannot install a replacement part that no longer exists. The greatest advantage may come from dividing the work. Robots are well suited to repeated inspections, known repairs, and jobs in places that are hot, cramped, or unsafe for people. Humans can spend more time on failures that don't match the manual, where the symptoms are confusing and several systems are affecting one another. Even then, the machines would need clear ways to show what they sensed and why they chose a repair. A crew cannot safely trust a diagnosis it has no way to check. So the fleet would scale labor only while the ship could keep that fleet supplied, aligned, and understandable. Building more robots would help if their common parts could be made aboard, and if their tools could still be measured against reliable standards. Building hundreds of machines around one irreplaceable sensor might only spread the same weakness into hundreds of bodies. Robots could therefore extend what each person can watch, lift, test, and repair. They might turn a few trained technicians into the working force of a much larger settlement, but every mechanical helper, draws from the same workshops and materials as the systems it protects, and that brings the problem down to a harder limit. Which parts can the ship still make when a replacement demands precision beyond its remaining tools? A replacement part can fit perfectly and still fail to fix the machine. The ship may have the right metal, a working printer, and a robot able to install it, yet none of those can tell the robot why the old part failed. That answer has to come from measurements, records, and a system that understands what the readings mean. Before any repair begins, sensors have to notice the fault. Test equipment then has to separate a broken component from bad wiring, a weak power supply, or a control command arriving at the wrong time. Those instruments also need calibration, which means checking them against a trusted standard. If that chain has drifted, the robot may follow its procedure exactly, while acting on false information. You get perfect obedience to a mistake. A pressure gauge offers a clear example. Suppose it reports that an oxygen line is losing pressure, so a maintenance robot replaces the valve named in its fault guide. If the gauge itself has aged and now reads low, the new valve changes nothing. The next procedure may blame the regulator and then the pump. Each repair consumes material and creates another chance for damage, while the original problem remains inside the instrument used to diagnose it. A very capable robot can spend the afternoon fixing everything except the fault. Software can help trace these failures, but it needs models of how the ship should behave. That includes wiring diagrams, expected temperature curves, service histories, known failure patterns, and records of past modifications. A machine built 2 centuries after launch may no longer match its first design. A cable may have been rerouted around a fire-damaged compartment. A pump controller may contain a patch written by someone whose name has vanished from the crew roster. Without that history, the robot sees the ship as it was planned, rather than the ship the crew actually lives inside. Some knowledge may never have been written down. An engineer might learn that a vibration is harmless until it changes pitch, or that a sensor gives a false alarm whenever a nearby motor starts. We pass details like these through demonstrations, corrections, and years of shared work. An autonomous system can preserve them only if someone records them clearly enough to be searched, tested, and revised as the machinery changes. It cannot recover missing context merely by printing another tool or copying an old repair guide. Repair, therefore, depends on more than workshops and stored material. The ship has to preserve its ability to sense accurately, compare readings with reliable standards, interpret faults, and remember why earlier crews changed the machinery. Lose enough of that chain, and automation becomes dangerously confident, precise hands carrying out the wrong repair. The hardest shortage may arrive before the metal runs out, when the ship still has parts to use but can no longer tell what is broken. A repair robot can diagnose the right fault, choose the right tool, and still be unable to save the machine. Before any repair begins, the ship must give it a stable place to work. The lights need to stay on. The air must remain safe around exposed equipment. Cooling has to carry heat away, and the power supply cannot lurch each time a motor starts or a damaged circuit is disconnected. This sounds less impressive than a robot rebuilding a pump with steady mechanical hands, yet it comes first. Maintenance only has meaning inside a working habitat. If a failed cooling loop lets a compartment overheat, delicate sensors may drift out of calibration while the robot is using them. If water reaches an electrical cabinet, restoring one device could energize a path through another. A machine that understands the broken part may still lack a safe moment to touch it. Human repair crews depend on the same background without noticing it very often. You notice the machine on the workbench, not all the larger systems holding its surroundings steady while the repair is underway. A workshop on Earth receives steady electricity from a much larger grid. Fresh air enters from outside. Waste heat leaves through walls, vents, cooling water, or the open sky. If one building becomes unsafe, people can step out and bring equipment from somewhere else. A ship between stars has no somewhere else. So the first condition for robotic repair isn't clever manipulation, it is continuity. Enough of the habitat must keep working for the robot's measurements to mean the same thing from 1 minute to the next. Enough power must remain available to isolate damage, run tests, move tools, and bring the repaired system back slowly. The ship must also protect the people who decide whether that return has gone as planned. This creates an awkward limit. Automation is often treated as the answer to systems that are too large or too complex for a small crew to maintain. Yet the more unstable the ship becomes, the less useful its automation may be. Robots don't stand outside the crisis. They breathe no air, but their processors need cooling. They eat no food, but their batteries need charging. They don't panic, though a failing sensor can still give them a false world to act upon. A successful repair, therefore, rests on a layer of success that came before it. The habitat has to preserve enough air circulation, electrical stability, cooling, access, and time for repair work to remain possible. That stability also has to last long enough for testing, because a repair that works for 10 seconds may fail as soon as the system carries its full load again. Once too many of those conditions fail together, the ship may still contain capable robots and shelves of perfect parts, while lacking the stable setting needed to use either one. That leaves the crew with a larger problem. If every machine depends on the habitat, and the habitat depends on thousands of machines continuing to cooperate, how can a ship keep its basic living systems stable for centuries? Water is one of those living systems, but it doesn't stay in one place long enough to be treated as a single supply. A cup drawn for drinking becomes moisture in someone's breath, sweat on their skin, or waste sent toward a treatment unit. Water used for washing joins another stream. Around the farms, it moves through roots, leaves, pipes, and the humid air. All of it belongs to the same circulating reserve. That makes the ship less like a house with several water bills, and more like one sealed habitat passing the same water from hand to hand. The crew drinks from it. The crops drink from it. Showers, kitchens, medical rooms, and cooling systems borrow from it, then depend on other machines to collect and clean what comes back. Even the moisture that gathers on a cold wall has to be caught, because water left there is water missing somewhere else. On Earth, a small leak can feel like an inconvenience. Fresh water can arrive through a pipe, fall from the sky, or be brought in by a repair crew. A generation ship has no river beyond its walls. If a seal releases a faint mist into a space where it can't be recovered, the loss may seem harmless that day. Yet the next round of drinking and irrigation begins with a little less water than the round before. The same is true when a filter holds water that can't be extracted, when damp material is discarded, or when vapor escapes during maintenance. None of these losses needs to be dramatic. Their danger comes from repetition. A fraction disappears, the smaller supply circulates again, and another fraction can disappear from that reduced amount. Over decades, tiny failures stop being tiny because every missing cup has been removed from all future uses of that cup. You don't lose it once, you lose every later use that water could have served. The loops also affect one another. Give more water to crops during a hot growing period, and less may be ready for washing or reserve storage until the plants release it back into the air. If humidity collectors fall behind, water gathers in the habitat while tanks run low. The ship hasn't lost that water yet, but it has lost access to it at the place and time where it is needed. A crew can be surrounded by damp air and still face a shortage in the irrigation lines. So water security isn't just a question of carrying enough at launch. The ship has to keep finding the same water, cleaning it, and returning it to use with almost nothing slipping away. Each person and plant becomes part of that circulation, whether anyone notices or not. For a century-long voyage, success means that a drink taken today can become tomorrow's shower, next week's crop water, and another person's drink years later. And if one shared supply has to serve everybody, farm and room aboard, who decides which need comes first when the loop begins to shrink? The International Space Station has shown that people can recover and reuse water far from Earth's rivers and reservoirs. After years of improvements, NASA reported that the station's water system could recover about 98% of the water available to it. That is a major achievement. Astronauts can drink water that once passed through cabin air, wash water, or urine because the station cleans it and sends it around again. Yet 98% is not a closed loop. If 100 gallons enter a recovery cycle, about 98 gallons return for use, while roughly 2 gallons remain outside the recovered supply. Some may stay trapped in waste or equipment. Some may be lost through steps the system cannot fully reverse. On the station, that missing water can be replaced when fresh supplies arrive from Earth. A ship traveling for 1,000 years would have no delivery waiting at the end of the month. Even if its equipment matched the station's best recovery figure, it would still need make-up water unless it could reclaim almost everything left behind. The amount lost would depend on how the ship handled waste and how often each portion passed through the equipment. It wouldn't disappear in one dramatic failure. Tiny amounts would slip from use each time the water went around. That difference in timescale can hide inside an impressive percentage. A system may work beautifully through a mission and still empty its supply across centuries, because each small loss is added to all the earlier ones, with nothing arriving to replace them. And the same water doesn't pass through only once. It may be recovered, used, and recovered again many times within a year. 98% recovery on each pass would therefore be very different from losing only 2% across the whole voyage. For the International Space Station, that figure marks years of careful engineering and steady improvement. For a sealed habitat without resupply, the remaining fraction would help determine how long the supply lasts. Engineers could reduce the loss, recover water from more kinds of waste, or carry extra reserves, but the 1,000-year requirement changes the standard. Almost closed is still open, and time keeps collecting whatever escapes. The station also has teams on Earth watching its pumps, filters, seals, and test results. Components can be replaced, new methods can be installed, and unexpected contamination can be examined by laboratories at home. Engineers can also compare samples over time and adjust the system when its performance begins to change. None of that takes away from what happens in orbit. It tells us what the achievement proves. High recovery is possible under close supervision, with replacement equipment and resupply still within reach. What it has not proved is that one supply can circulate for 1,000 years without continuing losses. A generation ship would need to plan for the water that stays in waste, clings to materials, escapes during repairs, or becomes too contaminated to recover. Once those small losses have had centuries to accumulate, how much reserve water would the ship need to carry? And the reserve water is only part of the burden. Every cup that returns to the ship's supply has to pass through a chain of equipment that separates water from everything people have mixed into it. That equipment does not simply sit there for centuries. It collects dirt, grows films of microbes, loses efficiency, and slowly uses up the materials that make treatment possible. Filters catch particles, but the trapped material has to go somewhere. As a filter fills, pumps must push harder to move the same amount of water through it. Eventually, the filter needs cleaning or replacement. A crew can wash some filters and reuse them, yet each cleaning can damage the fibers a little, while some contamination remains lodged too deeply to remove. Membranes face a similar problem. Their tiny passages can separate water from salts and dissolved waste, but those passages can become blocked or chemically damaged. Pressure may force water through, though higher pressure also demands more energy and places more strain on pumps, seals, and pipes. If a membrane tears, unwanted chemicals can cross into the cleaned water before anyone notices. And separation always leaves something behind. When water is pulled from urine, washing water, or damp waste, the remaining liquid becomes a concentrated brine. Recovering still more water makes that brine thicker and harder to process. Salts can form crusts inside pipes. Organic compounds can foul surfaces. At some point, the last fraction of water may cost more energy and treatment material than it is worth recovering. Microbes add another layer. Warm pipes carrying traces of nutrients are good places for bacteria and fungi to grow. Some form biofilms, thin living coats that cling to the inside of tanks and tubing. A disinfectant may control them for a while, but microbes can shelter beneath the film, and the disinfectant itself can react with other chemicals in the loop. Heat can kill them, though heating large flows again and again takes energy and wears equipment. Even after the particles, salts and microbes are handled, dissolved chemicals still remain. Treatment beds may use activated carbon, ion exchange resins, or other media that hold selected contaminants on their surfaces. Once those surfaces are full, the media must be regenerated or replaced. A ship cannot manufacture a fresh treatment bed by wishing the captured chemicals away. It needs raw material, energy, machinery, and a safe place for whatever regeneration removes from the water. This is the hidden structure beneath a high recovery rate. Spare membranes, fresh treatment media, cleaning chemicals, accurate sensors, pumps, storage for brine, and people who can tell when the water has changed before anyone becomes ill. The ship may recycle the water while slowly consuming the system that makes recycling work. The water, at least, begins as a substance the crew can collect, clean, test, and store. The air is less forgiving because every breath changes oxygen into carbon dioxide. How do you close that loop without slowly exhausting one gas or filling the ship with the other? A working water system does not give the ship a working oxygen system. Water contains oxygen atoms, of course, and electricity can split water into oxygen and hydrogen. You might think that means the loop is nearly closed. People breathe the oxygen, exhale carbon dioxide, and the machines turn the carbon dioxide back into something useful. Yet each step requires its own equipment, energy, chemical reactions, and somewhere for every atom to go. On the International Space Station, oxygen can be made by passing an electric current through water. The crew breathes the oxygen, while the hydrogen can enter another device with carbon dioxide removed from the cabin air. That reaction produces water, which can return to the water system. It also produces methane. Some of the oxygen comes back into circulation this way, but the methane carries hydrogen and carbon out of that loop when it is discarded. NASA describes this as partial closure because the gases and atoms do not simply circle forever. The crew must capture carbon dioxide and restore the oxygen it consumes. It must also keep enough hydrogen and return carbon to a usable form. A water recycler can work well while these other pathways remain incomplete. Plants seem to offer a softer answer. Give them light, water, and carbon dioxide, and they release oxygen while building new tissue. A greenhouse can therefore help clean the air and feed the crew at the same time. But the balance is demanding. Plants respire as well as photosynthesize, especially when the lights are off, and microbes consume oxygen while breaking down waste. Roots, soil substitutes, stored food, human bodies, and discarded plant matter all hold carbon in different forms. The air loop includes the whole living habitat. That is why oxygen recovery remains harder than the familiar image of a few green leaves in a sealed room. The machines and plants must match the crew's breathing through illness, crop failure, changing diets, maintenance periods, and shifts in electrical power. If carbon collects in a form the habitat cannot process, the loop has not closed. If hydrogen escapes with waste, water and oxygen production feel the loss later. The gases may look separate on a control screen, though the same atoms keep moving through air, water, food, bodies, and waste. A long-lived ship would need several conversion routes, with enough control to keep those movements in balance for far longer than any closed habitat has yet managed. NASA's current systems show that much of the cycle can be recovered, but they do not show a finished, sealed oxygen and carbon loop. The crew would still depend on active chemistry and biology every hour, and if air depends on a web of living and mechanical processes, how large and stable must that web become before a ship can truly feed itself? Methane is one way a ship could lose carbon without losing it all at once. Waste breaks down, microbes release gas, and some of that gas contains carbon that once belonged to food. If the methane is vented because the ship cannot safely store or process it, those carbon atoms leave the working cycle. They are still somewhere outside the hull, but they can no longer become another leaf, another meal, or another breath drawn through the life support system. That makes methane more than a waste gas. It is a small leak in the ship's ability to keep making life from the material it carried away from Earth. The loss may seem tiny during 1 week, especially beside tanks holding years of supplies. A generation ship has to live with the same leak through harvest after harvest, while replacement carbon remains far beyond reach. You would not see the farm fail when the first thin stream of methane escaped. The damage would appear slowly, as each growing season began with a little less carbon available than the one before. On Earth, escaped methane can re-enter the wider environment. A spacecraft has no such surroundings beyond the wall. Its usable world ends at the hull, so carbon that crosses that boundary is lost to the farm, even when nobody notices the amount that day. The same trouble appears whenever carbon settles into a form the recovery system cannot return to use. Some may remain in residues that plants cannot take up. Some may collect in material that is unsafe or too costly to process. A machine can report that most of the carbon was captured, while the uncaptured share continues to drain the whole system. Recovery is therefore about more than collecting matter. The ship must turn it back into forms that its plants, microbes, machines, and crew can use again. That distinction becomes severe over long voyages. Suppose a process returns almost everything sent through it. Each pass still leaves a fraction behind, and the recovered material does not simply sit in a tank forever. It moves through farms, meals, bodies, and waste, then comes around again. A small loss can meet the same limited store many times. The loop can look nearly closed at every pass while its total supply slowly shrinks. Engineers could reduce methane loss by capturing the gas and converting its carbon into something useful. Yet that adds equipment, energy demand, controls, and more places where the chain can fail. Keeping the gas aboard is not enough if its carbon remains trapped in a form the food system cannot accept. The full route has to work, from waste to recovered carbon and back into living tissue. So a ship may begin with enough carbon for its crew and still become poorer each year, not through one dramatic accident, but through thousands of incomplete returns. Once that slow erosion is included, how much biological machinery would the ship need to keep feeding everyone? The ship's biological machinery would be much larger than a room full of plants. It would include the people who eat them and the organisms that return waste to the growing cycle. Pumps moving water and air would also belong to that ecosystem, not sit outside it. That changes how we think about life support. A filter can be tested against a known flow of air. A crop can be measured by its harvest. Yet aboard a ship, neither works alone. The crew breathes out carbon dioxide for the crops. The crops release oxygen and become food. Microbes take apart what the crew and crops leave behind, returning some of it to forms that roots can use again. Pumps, lamps, pipes, and chemical processes keep those exchanges moving when biology cannot manage them by itself. Each part affects the others. If a crop grows slowly, it removes less carbon dioxide from the air and produces less food. If microbes break waste down too quickly, they may release nutrients faster than the crops can take them up. If conditions inside a processing tank shift, the wrong microbes can spread while the helpful ones fade. Nothing has to stop completely for the habitat to move away from balance. On Earth, ecosystems can absorb many changes because they are vast, varied, and open. Seeds arrive from elsewhere, animals move, rain carries material across whole regions, while rivers and winds connect places that seem separate. A ship has no neighboring valley to supply what its farms have lost. Its living world ends at the hull, apart from whatever stores the crew brought with them. The goal, then, would not be to freeze the habitat in one perfect state. Living systems never stay still. Populations rise and fall, harvests vary, and microbial communities change as they respond to food, temperature, moisture, and one another. The crew would need a system that can move without drifting so far that it cannot recover. That means keeping spare capacity across the habitat. Extra growing area could stop 1 week harvest from becoming a food shortage, while air treatment carries the crew until the crops recover. The nutrient cycle also needs another route. When one living process weakens or produces material the next cannot use. Across centuries, the crew would also become part of the maintenance cycle. Their bodies contain carbon, nitrogen, water, salts, and other material the habitat cannot afford to treat as waste. Births, deaths, illness, diet, and changing crop choices would all alter where those materials were held. The ecology would have to remain stable through human lives, not merely through engineering tests. Every reserve has a cost because the extra lamps and pumps draw power, while backup processing keeps tanks warm and fluids moving. Even when nothing is failing, balance consumes energy every hour of every year. So once the ship has built enough biological capacity to survive its own losses, how much power will remain for everything else? A generation ship could keep its lights on, its air moving, and its crew alive while still slipping into a kind of mechanical decline. Survival would take first claim on the power supply. Air circulation, water treatment, food production, temperature control, and medical equipment could not simply be turned off to free energy for repairs. That leaves every other task competing for what remains. A fabrication shop needs heat, motors, cutting tools, and control systems. Diagnostic equipment must energize sensors and run tests long enough to find a fault. Recycling machinery has to crush, separate, melt, clean, or reshape worn material. Even moving a heavy component through the ship may require powered lifts and sealed doors. None of those loads sounds impossible by itself. The trouble appears when they arrive together. A damaged pump may need a new bearing, but making that bearing requires a working furnace and machine tools. Those tools need cooling, clean air, and computers. The computers depend on electrical converters that may also be aging. Repair is never just one machine using one socket. It draws on a web of equipment that must all be available at once. You can see how the ship might become trapped. The crew still has enough power to breathe and eat, yet not enough spare capacity to rebuild the equipment that keeps breathing and eating possible. They can postpone a fabrication run, reduce testing, or strip parts from a less urgent system. Each choice buys time. It also makes the next repair harder. Recovery work is especially demanding because failures rarely wait for a calm day. If a water processor stops during a period of weak power production, the crew may need to run backup pumps while opening the main unit, testing its parts and manufacturing a replacement. The survival load rises at the same moment that the repair load arrives. A power system sized only for normal operation could fail this test without suffering any fault of its own. Stored energy can soften the blow. Batteries or other reserves could cover short bursts of heavy work, provided the ship had enough spare generation to recharge them afterward. If normal survival already consumes nearly everything being produced, the reserve becomes a bucket that can be emptied but not filled. It helps once, then slowly disappears from the crew's options. That loss may remain hidden for years, because the systems keeping people alive can continue running while the workshops behind them lose capability. This means power margin is not a luxury added after life support. It is part of life support stretched across time. Without it, the ship may look stable on a control panel while its ability to diagnose, rebuild, and recover is being spent away. The crew can survive today and still be losing tomorrow. So how much extra power would the ship need to carry for repairs that no designer could schedule centuries in advance? Voyager 1 has been running since 1977. Almost half a century later, it still speaks to Earth from beyond the planets, using a transmitter with less power than many household light bulbs. Engineers have kept it alive through failed parts, fading instruments, and computers built when memory was counted in thousands of bytes. Few machines have worked so far from home for so long. Its power comes from an RTG, a radioisotope thermoelectric generator. Plutonium inside the generator releases heat as it decays, and thermocouples turn some of that heat into electricity. There is no turbine or engine cycle, and there are almost no moving parts. With fewer things to wear out or seize, the generator can continue working for decades. Yet it cannot restore itself. The plutonium produces a little less heat each year, while the thermocouples slowly become less efficient. Voyager launched with roughly 470 watts of electrical power. That supply has fallen year after year, and nothing aboard can raise it to its earlier level. The spacecraft has lasted because the decline is slow enough for engineers on Earth to keep adapting. They have switched off heaters, retired instruments, and changed how the remaining equipment operates. In 2023, engineers began drawing on a small reserve of electrical power that had protected the spacecraft from voltage changes. Using it allowed more scientific instruments to remain active, though the decision also removed some protection. Each extra season of work is purchased by accepting a little less capability somewhere else. That is remarkable engineering, but it is not renewal. Voyager cannot make fresh plutonium, replace its aging thermocouples, or return the generator to its launch output. It remains alive by asking less from a shrinking supply, because engineers make those reductions slowly. Decline can resemble permanence when you look at the mission from a distance. The loss is controlled, but the lost capacity never comes back. A generation ship might still use similar designs where low maintenance is more important than efficiency. Long-lived radioisotope sources could keep emergency radios, isolated sensors, or buried control equipment running when larger systems were unavailable. A generator that loses power gradually gives a crew time to respond, and that time could prevent a local failure from spreading. The trouble begins when graceful decline is mistaken for self-repair. A ship carrying a whole human world cannot solve every shortage by shutting down another instrument, heater, workshop, or growing light. Eventually there is nothing expendable left. The passengers would need the means to recover lost generating capacity, rebuild the equipment that turns energy into electricity, and obtain another energy source without help from Earth. Voyager shows how durability can postpone that demand for an astonishingly long time. It also shows the limit with unusual clarity. Lasting is not the same as becoming whole again. So what kind of power system could make the parts and fuel needed to recover its strength? A power system cannot rebuild itself by supplying electricity alone. Once a damaged generator needs a new bearing, a fresh seal, or a replacement control board, the ship must do more than find enough watts. It must preserve the chain of equipment that can turn raw stock into a working part. That chain begins farther back than a repair bench. A worn bearing may require a furnace that can melt metal, a machine that can shape it, gauges that can measure it, and instruments that can check for flaws hidden below the surface. Each machine depends on smaller parts of its own. The gauge needs sensors. The furnace needs insulation. The cutting tool needs a harder edge than the piece it cuts. Even the lubricant has to come from somewhere. This is where repair stops being a person with a wrench and becomes an industrial system. On Earth, that system is spread across mines, refineries, factories, laboratories, warehouses, and thousands of companies. A ship cannot carry that entire network in miniature. Yet if it leaves out one critical link, a small failure may eventually reach something the crew can no longer reproduce. Recycling helps, though it does not make the problem disappear. Metal from a retired pump can become feedstock for another part, and chemicals can be recovered from equipment that has reached the end of its life. But every recovery step uses energy. Materials can become mixed, contaminated, or lost in places where collecting them costs more than the ship can spare. A closed loop is never perfectly closed. The crew also has to know what they are looking at. A cracked housing is easy to see. A transistor that fails only when warm is harder. Finding that fault may require test equipment, reference samples, software, and people who understand how the signals should behave. If the diagnostic tool breaks, the ship may need another diagnostic tool to find out why. You can feel the faint absurdity in that. The machine that identifies broken machines can become the broken machine everyone is waiting on. As the energy surplus narrows, these layers begin competing with daily life. Running a furnace may mean delaying another production job. Keeping a clean manufacturing space may take power from cooling or food storage. The ship can ration those demands for a while, but repeated delays allow damage to gather faster than the workshops can clear it. We are no longer counting separate repairs. We are asking whether the ship can preserve the means to repair at all. The survival problem is no longer just whether one reactor can run for centuries. It is whether the ship can keep enough connected capability alive to diagnose failures, recover usable material, make precise replacements, and restore the machines that do the making. Which parts of that industrial ladder must travel with the ship, and which missing rung would bring the whole climb to an end? A failed pump might seem to need one replacement part, perhaps a new impeller shaped to match the worn one. The workshop has the drawing, and the crew has a machine that can cut metal. From a distance, that looks like a complete repair, yet the impeller is only the final object in a much longer chain. The drawing does not supply the material, protect the cutter, or prove the result. Before cutting begins, someone has to identify the right material. Metal can have the correct shape and still crack under load because its internal structure is wrong. The workshop may need a specific alloy, mixed in controlled amounts, melted without contamination, then cooled or heat-treated at a set rate. That requires furnaces, temperature sensors, clean containers, and feedstock with a known history. Scrap from another machine may work, but only if the crew knows what it contains. Recycled metal also has to be sorted, cleaned, and sometimes refined before it reaches the furnace. Then there is the cutting machine. It depends on bearings, motors, lubricants, control systems, and edges harder than the material being shaped. Those edges wear down, bearings lose accuracy, and coolant gathers metal dust. Making an impeller slowly consumes the machine that makes impellers, so the workshop needs some way to restore its own tools. A workshop that cannot service its cutting machine is only borrowing time from it. Even a finished part isn't ready until someone checks it. A smooth surface may hide a crack. A shaft cut slightly too wide may bind as it warms, while one cut too narrow may shake itself apart. The crew needs accurate gauges, working inspection equipment, and reference standards for testing those gauges. Without them, you can make a faulty part with complete confidence and discover the error only when the pump fails again. Inspection is not paperwork added after making. It is part of making the part at all. People connect every rung. Someone must understand the pump, someone else must know the alloy, and an operator must recognize the sound of a cutting tool beginning to chatter. Written instructions help, but they can't hold every judgment gained through years of practice. Skills fade when they're rarely used. A repair needed once every 40 years may fall to people who have never seen it done, using equipment maintained by crews who learned from records instead of teachers. That is why spare parts cover only the early failures. A warehouse can hold impellers, seals, valves, and bearings, but no inventory can anticipate every break across centuries. Eventually, the ship must make something it didn't bring. That means preserving material knowledge, working tools, trustworthy measurements, and trained hands. Behind each one stands another workshop, another supply, or another skill. The replacement part is only the visible end of the repair. Beneath it sits the ability to prepare the material, restore the tool, test the result, and train the next operator. If the ship can't reproduce those supporting abilities, its machines become things that can still be used, but not renewed. So how much of an industrial world must travel with the crew before the ship can keep making itself? The ship does not need to carry every factory found on Earth. It does, however, need a small industrial chain that can repair its own links. A machine shop without metal is helpless. A refinery without working pumps soon becomes helpless too. The threshold comes when enough of these systems can support and rebuild one another. It begins with extraction. Material may come from worn parts, damaged structures, stored ore, or perhaps an asteroid encountered along the way. Recycling would probably provide much of the early supply, since a broken motor still contains copper, steel, magnets, and other valuable material. Yet recovering them means separating mixtures that were never designed to come apart after centuries of use. Even a discarded cable can become a stubborn knot of metal, plastic, insulation, and grime. The recovered material then has to be refined. Metal contaminated with oil, corrosion, or fragments of another alloy may look usable while behaving badly under heat or strain. Ceramics and polymers bring different problems. The crew must identify each batch, remove what does not belong, and bring its composition close enough to what the next process requires. Close enough is not guesswork. It depends on tests the crew can still trust. Only then can fabrication begin. Furnaces melt and treat metals, while machine tools cut them into exact shapes. Other equipment forms wire, glass, seals, circuit boards, and the less glamorous pieces that keep air moving and water clean. These processes do not need to match the full range of industry on Earth. They need to cover the ship's key materials, and produce the parts that other workshops depend on. Inspection closes the loop. A new pressure vessel can appear flawless and still contain a hidden crack. A bearing made a fraction too large may overheat after installation. The ship therefore needs instruments that measure dimensions, composition, strength, electrical behavior, and internal damage. Those instruments also require calibration against stable references. If the reference drifts, a wrong measurement can be repeated with complete confidence until an entire batch has been spoiled. And this is where repair begins to resemble limited self-reproduction. The furnace helps make parts for the lathe makes fittings for the refinery prepares material for the instruments, while those instruments check the next furnace component. No single workshop makes the ship independent. Their value comes from the closed paths between them, each keeping some part of the others alive. Some gaps may remain. The crew could carry rare catalysts, advanced computer chips, or specialized medicines in quantities meant to last, accepting that these are beyond local production. The aim is not perfect independence. It is to shorten the list of losses that cannot be recovered, while protecting the few supplies that still have no replacement. And that list would never stay fixed. Designs would change, materials would age, and skills could fade between generations. A workable industrial core, therefore, depends on people who can adapt it without slowly damaging the web of support underneath. How do you preserve that kind of knowledge when every expert who left Earth is long gone? A ship like this is carrying far more than people and machines. It is carrying a limited civilization cut away from the larger one that built it. Earth can spread a difficult task across mines, factories, universities, suppliers, repair shops, and millions of workers. The ship has to preserve a much smaller version of that connected system, with no neighboring country to call when a part fails. That changes what survival means. Food, air, and water keep the crew alive from one day to the next, while industrial capability keeps those life support systems repairable across generations. A farm can feed people only while its pumps, lights, sensors, and nutrient control still work. A workshop can repair those parts only while it has suitable materials, accurate instruments, dependable power, and people who understand the process. Each layer rests on several others. The central mission is to keep enough of this web working that damage remains recoverable. The crew doesn't need to reproduce every product Earth once made. It does need the ability to diagnose failures, make replacements that are good enough, check that those replacements are safe, and teach the whole chain again before the knowledge disappears. You could call that technical life, the continuing ability to make, test, repair, and learn, rather than a storehouse of clever objects. A civilization in transit would have to choose its habits with the same care it chooses its machines. Maintenance cannot become work that only a few specialists understand. Measurements need shared standards, and failed repairs need records that later crews can read. Apprentices need time to practice before an emergency leaves no room for mistakes. When a process changes, someone must also understand which other processes now depend on the new version. There is a very human difficulty inside that arrangement. We grow tired of rules when their original reason has faded. A cleaning step may look wasteful after 50 years without contamination. A calibration check may feel excessive after 1,000 successful parts. Yet removing one dull step can introduce an error that stays hidden until a pressure vessel cracks or a crop system begins dosing the wrong amount. Process discipline is often least appealing when it has worked well for a long time. The ship, therefore, carries a culture of production as much as a set of production tools. It needs people who can challenge old methods without forgetting why those methods existed, and people willing to preserve knowledge they may never use themselves. Some generations will inherit machines designed centuries before their birth, then pass them onward to descendants they will never meet. Even so, no crew can preserve every branch of Earth's industry at equal depth. Space, energy, labor, and training are limited, while some materials require long chemical chains or extreme precision before they become usable. The ship may remain very good at making metal structures while losing the ability to replace one small flexible seal. So which classes of material are hardest for a traveling civilization to keep reproducible? A steel beam and a rubber seal can weigh the same, yet they create very different problems for a ship. Steel can be melted, cleaned, tested and cast again. The atoms survive the life of the part. If the crew has enough heat and the right equipment, yesterday's broken bracket can become tomorrow's useful plate. Glass behaves in much the same way. A cracked window cannot simply be pressed back together, but its material remains available. It can be crushed, melted, refined, and formed into something new. Some ingredients will be lost, and contamination can spoil a batch, yet the basic root is clear. The ship is holding both an object and much of the raw material needed for its replacement. Flexible materials are less cooperative. A seal may begin as several chemicals mixed in exact amounts, then cured under controlled heat and pressure. During curing, the molecules link together into a structure that cannot be melted back into its starting ingredients. Grinding the old seal into crumbs does not recover fresh rubber. It gives you crumbs. That difference is easy to miss when everything is counted only by mass. The ship may contain tons of carbon, hydrogen, oxygen and sulfur, but those elements are not waiting in tidy containers. They are tied up in food, waste, insulation, paint, medicine, cable coverings, and thousands of other compounds. Recovering the right atoms is only the first step. The crew must also rebuild the chemical chain that gives a new material its strength, flexibility, and resistance to heat. Lubricants create another version of the problem. A machine may need an oil that stays fluid in deep cold, does not evaporate in low pressure, and does not attack nearby plastics. Used oil can sometimes be filtered and restored, though heat slowly changes its molecules. After enough cycles, the ship needs more than a filter. It needs the ability to make the oil again. Catalysts can be even less forgiving. They may contain only a small amount of platinum, nickel, or another active material, spread across a carefully prepared surface. The metal might be recoverable, yet the microscopic structure that made it work can be lost. Having the element is not the same as having the catalyst. Specialty polymers bring all these difficulties together. Their recipes may depend on pure feedstocks, tightly controlled reactions, and additives used in tiny amounts. A missing stabilizer could leave a cable coating brittle. A slightly different seal might swell in contact with fuel. The substitute can look correct and still fail inside a wall where nobody can inspect it. So the ship's material store is not one large bank that can pay for any replacement. Metals and glass may circulate through repeated lives, while some chemicals become harder to reclaim each time they're used. The most dangerous shortage may be measured in grams, hidden inside a part that keeps air in or coolant out. How does a crew decide which fragile materials deserve an entire chain of machines, skills and reserves? A ship can have plenty of steel and still lose the ability to make a good bearing. The problem begins with precision. A bearing is not merely a ring of metal shaped to roughly the right size. Its surfaces must be smooth within a known limit, its curves must match, and its hardness must fall inside a narrow range. If any one of those slips, friction rises, heat builds, and a machine that should run for years may wear out in months. Making the part requires another layer of exactness. The cutting tool has to hold its shape. The lathe must turn without a hidden wobble. The instrument used to measure the finished surface must itself be checked against something more accurate. That more accurate standard needs checking too. This is a calibration chain, and every link depends on those behind it. On Earth, we rarely see how much of that chain sits out of sight. A factory can send a gauge to a specialist laboratory, order a certified reference block, or replace a sensor whose readings have begun to drift. A ship cannot reach beyond itself. If its best reference is damaged, later measurements may remain consistent while becoming wrong. Every gauge agrees because every gauge inherited the same small error. Cleanliness works in much the same way. Some electronic parts, optical coatings, medicines and catalysts can be ruined by traces too small to see. A film of oil, a grain of dust, or a few unwanted atoms in a chemical bath may alter the result. Producing a clean surface requires filtered air, controlled water, suitable solvents, seals that do not shed particles, and instruments able to detect contamination. The metal for the chamber may still be stacked in storage, while the ability to reproduce its cleanliness has already faded. Catalysts create another weak point. They help chemical reactions proceed without being consumed in the simple sense. Yet they can still become poisoned, coated, or slowly lost during processing. Recovering them may demand temperatures, pressures, and separation steps that rely on calibrated equipment. The crew might possess kilograms of the right element, but no longer know how to prepare its surface so that it works. Even the people doing this work need living standards to compare against. A technician learns what a healthy machine sounds like, and what a polished surface should feel like. But touch and memory cannot replace every measurement. Written procedures help, though a procedure can preserve the steps while the reason for one small limit disappears. Someone widens that limit to keep production moving. The next workshop accepts the new parts, and a lower level of precision becomes normal. Precision behaves like a shared utility. Once it falls, many workshops decline together, even if none has suffered a dramatic failure. The ship may still melt metal, cast shapes, and build machines. It just cannot make them repeatably enough to support the machines that make the next generation. If a civilization aboard the ship can lose capability without losing its raw materials, how would its crew know which forms of precision must never be allowed to slip? A crew facing that problem might first try to preserve every machine exactly as it left Earth. That sounds sensible. The ship was designed as a complete system, and changing one part could disturb 10 others. Yet, after several centuries, exact preservation may become the more dangerous choice. A machine that depends on a coating nobody can make, or a sensor that only one aging instrument can calibrate, is already living on borrowed time. The better response may be to redesign it. That choice would need repeated testing, because a simpler machine can still fail in unfamiliar and dangerous ways. Suppose a pump uses a highly efficient seal made from a rare polymer. The crew can search its stores for replacements, then spend years trying to recreate the chemistry. Or its engineers can accept a pump that leaks a little more and uses more power, but works with a seal they can produce in any capable workshop. On Earth, that replacement might look crude. Aboard the ship, it could be the more advanced design because the crew can understand it, test it, and make another one. This changes what success means. The goal is no longer to keep every launch error machine alive. It is to keep each necessary function within reach of the ship's present abilities. Cooling still has to work, water still has to move, and air still has to circulate. Yet the machines doing those jobs may grow heavier, slower, and less efficient as their hidden dependencies are removed. We already use versions of this approach where repair is difficult. Equipment made for remote places often favors common fasteners, replaceable modules, and parts that can survive dust or rough handling. A generation ship would have a stronger reason to follow the same path. Every component would need to be judged not only by how well it performs today, but by whether people can reproduce it after its factory, software, and experts are gone. Some losses could even make the ship easier to sustain. Fewer material types mean fewer recipes to preserve. Wider tolerances place less strain on measuring tools. A motor built to survive imperfect bearings may waste electricity, but it also stops one damaged grinding machine from threatening the air system. Efficiency can sometimes be recovered elsewhere. A vanished manufacturing chain cannot. There would still be limits. Simplification cannot turn any available substance into a safe catalyst, a sterile medical surface, or a window that survives years of radiation. Some functions remain tied to demanding materials, and those chains would deserve the ship's best protection. The crew would have to decide which complexity provides something irreplaceable, and which complexity merely saves weight, energy, or time. Over generations, the surviving ship may look less like the vessel that left Earth. Its systems would be rebuilt around what its workshops can reliably make, until repairability becomes part of every design. That may keep the machinery running. But when the same pressure reaches medicine, farming, and human bodies, what can the crew simplify without making life aboard the ship more fragile? The ship's computers would not simply grow old as a motor wears down. For centuries, Radiation would damage electronic parts. It could also corrupt stored information or make a working circuit follow the wrong instruction. Some damage builds slowly. Energetic particles pass through insulating layers and leave tiny electrical changes behind. Over enough time, a sensor may drift, a memory chip may become less reliable, or a processor may need more power to do the same job. Shielding can reduce that exposure, but it cannot stop every particle, especially when every added layer increases the ship's mass. Other failures arrive without warning. A charged particle can strike a memory cell and flip a bit from 0 to 1. It may change a number, alter a command, or crash a control system even though the hardware is still usable. Engineers call this a single event upset. The name sounds mild. It feels rather different when you remember that the affected computer may control air circulation, a reactor, or the ship's position. Spacecraft designers already protect against this. They use radiation-hardened components, duplicate critical computers, compare their answers, and check stored data for errors. If one machine reports something strange, another can catch it. Software can restart a failed process, while protected memory can correct some flipped bits before they cause trouble. None of this makes the computer immune. It makes a passing particle less likely to become a disaster. A generation ship would need those defenses to work far longer than any current mission. It could carry spare boards and chips, but spares also receive radiation unless they are heavily protected. Eventually, the crew would have to replace parts that no factory aboard the ship was built to produce. That is where electronics differ from pipes, brackets, and gears. A machine shop can cut metal into a new valve body. It cannot easily make a modern processor. That job needs extremely pure material, patterns too small to see, and specialized equipment whose own computers may already be failing. The ship might manufacture simple circuits, yet remain unable to reproduce the hardened devices designed on Earth. The problem extends beyond broken parts. A processor can still work while becoming impossible to replace, because its design tools, production line, or compatible components no longer exist. Engineers call that obsolescence. On the ship, it would mean maintaining old control systems long after their original supply chain had vanished, perhaps without anyone who had seen the first version operate. The crew may choose simpler electronics for vital machinery, keep several kinds of backups, and preserve ways to run essential systems with less computing power. That costs efficiency and may limit later upgrades, but it gives future technicians something they can understand, test, and rebuild. Even then, no electronic system can be trusted forever. If the ship must slowly redesign its controls around parts it can still make, who decides when a proven old system has become more dangerous than an untested replacement? A future machine shop may look reassuringly familiar. A worn hinge comes through the door, and a technician measures it, adds metal where years of use have thinned it, then cuts the joint back into shape. A cracked bracket might be copied from scrap. A pump housing could be opened, cleaned, patched, and tested under pressure. None of this would be easy, but you could still follow the path from damage to repair with your own eyes. Electronics hide most of that path. A failed sensor may be smaller than a fingernail, sealed inside a machine that cannot safely run without it. The sensor does more than fit a hole. It must turn heat, pressure, motion, or chemical traces into a dependable electrical signal. Making another one could require prepared material and dust-free tools that build tiny layers. The crew would also need equipment that can detect whether the finished part changes as it ages. Memory and microcontrollers reach further into the missing industrial world. Their microscopic circuits begin with exceptionally pure material and pass through many tightly controlled steps. Each step depends on machines that have their own sensors, control boards, pumps, chemicals, filters, and replacement parts. The workshop can remake a steel bracket because the bracket does not contain a hidden factory, a microcontroller does. Even a part that appears to work can still be wrong in ways the crew cannot see. A memory chip might pass a quick test, then lose stored data after months of radiation exposure. A control device might behave well at room temperature but fail when a motor starts, the voltage dips, or charged particles strike its circuits. Space radiation can flip bits, damage insulating layers, and slowly change how electronic parts respond. Hardened hardware reduces those risks, but producing it requires more than copying the shape of an old chip. It also has to be checked. Engineers on Earth can expose components to radiation, heat, vibration, and long operating cycles before trusting them inside spacecraft. A ship trying to reproduce that confidence would need test equipment, known reference samples, careful records, and enough spare parts to destroy some during testing. The crew would be building both the component and the means to prove that component's safe. This creates an awkward split in repair culture. The machine shop may grow highly capable, turning damaged metal into useful parts with skill that would impress the ship's first builders. Yet a silent chip on the same workbench could remain beyond reach. Technicians might replace a complex controller with relays, mechanical governors, or larger circuits they can inspect and reproduce. Those substitutes may weigh more and consume more power, while giving human hands a way back into the machine. Over centuries, that choice would shape the ship itself. Systems designed around tiny sealed electronics might gradually become larger, slower, and easier to examine. Repairs would become more visible, even as the machines became less capable. But how much performance can the ship surrender before repairability begins to threaten the mission it was meant to protect? The answer may depend on what the ship is willing to call good enough. A control system that uses little power and responds in a fraction of a second is valuable when replacements still arrive from a factory. Centuries later, speed means less if one failed component can silence the whole machine. The slower system may survive because the crew can see how it works, find the damaged part, and make another. You can see the change in what engineers would ask of each design. Instead of expecting each new controller to do more, they may need it to reveal more. Its parts could be larger, its connections easier to trace, and its behavior simple enough to test with equipment made aboard the ship. A fault would leave clues that a technician could follow, rather than a sealed black box that merely stopped answering. None of this makes the simpler machine better in every way. Mechanical governors wear at their contact points, relays click, heat up, and eventually fail. Larger circuits need more material, while backup units take space that could have held food, shielding, or spare pumps. The benefit is not perfection. It is the ability to inspect a failure, understand it, and build the replacement without depending on a vanished industry. Radiation adds pressure to make that trade. Charged particles can damage electronic components, alter stored information, and produce faults that are hard to predict. Shielding helps, and duplicated controllers can take over when one fails, but both demand mass and resources. A less advanced controller may still be vulnerable, yet its failure can be easier to locate. If the crew can replace one damaged board instead of discarding an entire sealed unit, the ship retains a path back to working order. Over time, the same logic could spread through steering, air circulation, farming equipment, and power control. The crew might reserve its most capable electronics for jobs that truly require them, while moving basic functions onto systems that can be rebuilt from local materials. That would create layers of technology aboard the same ship. A small number of advanced machines, surrounded by slower equipment designed to remain understandable. There is a human cost hidden inside that arrangement. People raised with fast automatic systems may have to accept controls that demand attention, patience, and frequent adjustment. A valve might need watching. A motor might need a person to hear when its rhythm changes. The ship would lose some convenience as it gained ways to recover, and daily work could grow heavier even while the chance of long-term survival improves. So the ship that reaches its destination may not be the ship its builders hoped to preserve. It may be less efficient, less precise, and far more dependent on human care. Yet it could still keep its air moving and its course steady because its machines remain within reach of the people who need them. If survival changes the ship this deeply, what does it do to the lives and society carried inside it? The people aboard the ship would not live beside its life support system. They would be inside it, along with the crops, the bacteria in their bodies, the microbes treating their waste, and every scrap of food moving back through the cycle. None of these parts could remain healthy alone. The habitat would work only if they kept working together. A farm would do more than feed the crew. Its plants would refresh the air while their roots shared the habitat with other life. Waste from crops and people would have to return safely to the next growing cycle. You might prefer not to consider that connection during dinner, but the ship could never afford to forget it. Those loops would never run by themselves. People would watch the habitat and intervene when water, crops, or equipment began to change. Their daily work and family lives would be part of that care. Maintenance could not remain one department serving everyone else, because human strain could eventually become an engineering problem. The reverse would be true as well. If a pump failed, crops could lose water. If crops failed, meals would shrink and oxygen control would become harder. Poor nutrition could weaken the people expected to repair the pump, while stress and lost sleep made mistakes more likely. A small fault could pass through the habitat, changing from a mechanical problem into a biological one, then a social one, before returning to the machinery. Microbes would make this harder to control. Some would support digestion and the return of waste to crops, while others could spoil food or cause disease. Sterilizing everything would destroy living processes the habitat needs. The crew would have to manage this invisible community instead. Even the number of available workers would depend on this shared health. Someone recovering from illness could not spend the same hours repairing pumps or tending crops. A failed harvest could leave fewer people strong enough to handle heavy work. When the habitat weakened, its ability to restore itself could weaken with it. That makes the residents part of the repair system. Their bodies provide labor, yet their health depends on the very loops they maintain. Their knowledge must survive long enough to guide children who will inherit jobs they never chose. Even sanitation becomes a form of engineering, because clean hands, safe food, and controlled waste protect the people who keep the ship alive. A generation ship is less like a vehicle carrying passengers than a habitat carrying its own caretakers. If every person is both someone to protect and part of the system doing the protecting, how would that shape the society they build? The first biological failure aboard a century ship may not look like a crisis at all. It may look like one crew member taking longer to recover from an infection, another losing strength a little earlier, and a harvest coming in slightly smaller than the last one. No alarm sounds. Nothing has broken open. Yet the ship is becoming less capable, one tired person and one weak crop at a time. Radiation makes that slow decline especially hard to read. Shielding can reduce exposure, but it cannot make a deep space habitat identical to Earth. Over decades, damage may collect inside cells even when no one feels sick today. Cancer is one concern, though it is not the only one. Blood-forming tissue, the nervous system, and the eyes can also be affected. A person may remain alive and active while becoming less able to work, heal, or withstand another strain. The clinic may see separate cases while the ship is actually accumulating a shared health debt. Then there is reproduction, where the uncertainty becomes more personal. We have no human record of conception, pregnancy, birth, and childhood across many generations under reduced gravity and chronic space radiation. Animal studies can reveal possible risks, but they cannot settle what would happen to people living their whole lives away from Earth. A ship could depart with healthy adults and still have no firm answer about the health of their grandchildren. Each successful birth would bring relief, but it would not prove that the next pregnancy or the next generation faced the same odds. Immune systems add another layer. Isolation does not mean freedom from microbes, because bacteria, fungi, and viruses would travel with the crew. Some are essential. Others can cause disease when stress, poor sleep, poor nutrition, or radiation weakens the body's defenses. Even a mild infection becomes costly when several people are tired at once and there is no replacement crew nearby. Care takes hours from healthy workers, and the caregivers may then become worn down themselves. The farms would carry their own health debt. A crop does not need to die for the change to hurt. It may grow more slowly, produce fewer seeds, or become more vulnerable to a fungus once kept under control. Less food then puts more strain on human bodies, while weaker people have less time and energy to protect the crops. The loss moves around the habitat before anyone can point to a single cause. This is how a ship can remain open, lit, and apparently stable while its ability to recover keeps shrinking. More hours go into care, fewer people can handle demanding repairs. Parents may begin to doubt whether the next generation will be healthy enough to inherit the work. And children may grow up knowing that their bodies are part of a long experiment no one aboard chose to begin. By the time the decline becomes visible, it may already connect human health to the farms that sustain it. So what kind of society forms when preserving health also means deciding whose risks the mission can afford and what that decision means for work and children? A generation ship could answer that pressure by treating health as a private concern. Each person visits the clinic, follows advice, and returns to work. That may help for a while, but it misses what the ship is trying to preserve. Healthy people today are not enough. The crew must keep raising and training people who can protect everyone's health tomorrow, even after the first experts are gone. Medicine becomes more than a clinic stocked with drugs. It has to train new nurses, doctors, lab workers, and caregivers before the older ones retire or die. They need practice, not just books. A young healer must learn how illness appears in this particular habitat, where the same headache might come from infection, stress, a failing air system, or months of poor nutrition. If only one person can tell the difference, the ship has a hidden point of failure. The farms face the same problem. Growing food inside a closed habitat is skilled work, shaped by local seeds, recycled water, changing soil microbes, and equipment that may have been repaired many times. You can read how wheat grows and still be unprepared for a weak harvest under the ship's lamps. Skill comes from seasons of watching, trying, failing safely, and working beside someone who has seen the problem before. Even parenthood carries part of the maintenance burden. Children need food, care, trust, and enough time with adults to become steady members of the crew. Parents cannot provide all of that alone, while also covering long shifts in the farms, clinic, or repair teams. The ship would need ways to share care without turning childhood into workforce preparation. These children are people growing up, not replacement parts. Their curiosity, friendships, and sense of safety are part of what allows learning to continue. Education ties all of this together, though a classroom by itself cannot do the job. Lessons have to lead into supervised work, and supervised work has to leave room for mistakes that do not poison a crop or harm a patient. Teachers must notice who is struggling, who is ready for more responsibility, and which skills are becoming rare. That takes time from experts whose labor is already needed elsewhere. It also means the crew must protect time for teaching, even when a damaged pump or crowded clinic makes every available pair of hands seem urgent. The result is a second life support system running through the first. Physical systems preserve water and food, while institutions preserve the ability to operate them. A ship may carry medicine and seed for decades, yet still lose the human chain that knows how to adapt and pass on that knowledge. That chain is delicate because knowledge does not pass intact merely because someone wrote it down. It survives through memory, practice, correction, and relationships between people of different ages. If one generation stops teaching well, the machines may continue humming while the crew's understanding thins beneath them. How much can be forgotten before a functioning world no longer knows how to maintain itself? A maintenance manual can tell you how to replace a failing pump. It can name the tools, show the order of the parts, and list the readings that should appear when the work is done. That is enough when the pump fails in the expected way. The correct tool still exists, and every reading means what its writer thought it meant. After 400 years, those conditions may no longer hold. Rebuilt parts may behave differently, and the named tool may have vanished long ago. The written procedure can remain accurate to a machine that no longer exists. An experienced technician handles this gap through judgment. She notices that the vibration feels wrong before any alarm sounds. She knows which faint smell belongs to a warm bearing and which one comes from harmless dust. If two gauges disagree, she does not simply trust the one with the brighter display. She asks what else changed, who worked nearby, and whether a repair made last month could be affecting the system now. Much of that skill is hard to place in an archive because the technician may not know how much she knows. Years of small corrections have taught her where to look and when to doubt the obvious answer. Asked to explain it, she might give a few clear rules. Then a trainee follows those rules and misses the weak signal that would have caught the fault early. Practice reveals what the manual leaves out. A trainee watches, tries, makes a mistake, and hears why the mistake was tempting. The lesson includes timing, sound, resistance under the hand, and the habit of pausing when several minor changes arrive together. None of those clues is magic. They are observations shaped by repeated contact with the same equipment and by correction from someone who has seen it misbehave before. Archives can help. Video may preserve a repair in motion, while recorded case notes can show how earlier crews solved rare failures. Simulators can expose trainees to faults that would be too dangerous to create in the working ship. Yet every record comes from a past version of the system. Someone still has to decide whether today's strange reading matches an old case or only resembles it. That difference becomes dangerous when trouble spreads slowly. Several small changes may each remain within their allowed limits and look harmless alone. A skilled crew may notice that they began together and trace them to one drifting control system. A crew trained only to check the manual may approve every reading. Stored knowledge can preserve the steps. Keeping the ship understandable requires people who can see when the steps no longer fit. And that ability must be rebuilt in every generation, even as the machines, tools, and conditions keep changing beneath their hands. Once skill can fade, governance becomes part of the machinery. The ship may have reliable pumps and careful manuals, yet still fail because nobody had to train a replacement before the last expert retired. A rule about apprentices can be as important as the strength of a pipe. That changes how the crew should think about staffing. It isn't enough to count the engineers alive today. They need to know how many people can diagnose each critical system, how old they are, and how long a beginner needs to become dependable without close supervision. If one technician understands the reactor controls, that system has a human single point of failure. Ships already treat vital hardware this way. 2 pumps may share the work, so either one can carry the load alone. Human skill needs similar backup. Though copying a person is harder than installing another pump, an apprentice needs time, real practice, and permission to make small mistakes, while an experienced hand can still catch them. That permission can feel wasteful. Training slows a job down. Audits interrupt routines that seem to work, while rotating people through unfamiliar duties can make a capable crew less efficient for a while. You can hear the complaint already. Why let the trainee touch it when Mara can finish in half the time? Because Mara won't be there forever. A stable institution accepts that short-term cost as part of keeping the ship alive. It schedules overlap between generations, protects teaching time, and checks whether a trainee can solve faults instead of merely repeating a procedure. It also makes experts explain their choices, which can expose habits that worked for years without anyone knowing why. The records must follow the living practice. If the crew modifies a valve, changes a crop cycle, or learns that a sensor gives false warnings under certain conditions, the lesson cannot remain in one person's memory. Someone has to test the finding, record it, and make sure the next training group uses it. Otherwise, the archive slowly separates from the ship it describes. Audits can measure that separation. A team might repair a system from the approved instructions, while an experienced observer watches. If the instructions omit a tool, hide a judgment call, or assume knowledge that newcomers lack, the failure appears during the exercise instead of during an emergency. Even a successful drill may reveal that everyone depended on the same aging expert. Authority shapes what people report as well. If admitting uncertainty brings shame or lost status, workers will hide gaps until a machine forces the issue. If promotions reward people who teach, document mistakes, and train capable successors, knowledge moves instead of collecting around a few protected roles. Social rules alter the ship's technical risk. The engineering model, therefore, has to measure whether skills will survive. Training time matters, as does overlap between generations and proof that more than one person can handle a critical task. The crew can test these conditions and give them safety limits. The ship survives only if its institutions produce competence faster than age, change, and complacency remove it. Governance isn't placed above life support. It is part of life support. A ship that manages all of this may still reach its destination with fewer abilities than it had at launch. We shouldn't call that voyage a failure. It may be the main reason anyone arrives alive. The first generation would inherit machines built by a civilization spread across Earth. Later generations would have only what fits inside the ship. Even with excellent records and training, they could not keep that whole technical world alive. A process might remain understood in theory, but still demand material or precision the ship could no longer produce. The response would be to simplify on purpose. Engineers might replace a highly efficient pump with one that uses more power but can be cast, machined and repaired aboard. A sensor that relies on a rare coating could give way to a less sensitive design made from materials already moving through the ship's workshops. Software might lose features so that a smaller group could inspect the whole system and know what it was doing. Each change would cost something. The new pump could draw more electricity. The simpler sensor could miss small shifts that its predecessor caught. Yet, a device the crew can rebuild is safer than a better device they can only watch grow old. This would make the ship's design a moving target. Every few decades, its people would need to ask which systems they could still reproduce with confidence, which ones had become fragile, and which functions could be combined or removed. They wouldn't be preserving a museum of launch-era engineering. They would be trimming the ship back to a form that still matched their tools, materials, and living skill. That change would reach beyond machinery. Education would focus on knowledge the ship could use, and workshops would favor forgiving methods. Research would turn toward local problems, because a discovery offers little help when it depends on capabilities that exist only in old records. Over centuries, the people aboard might become less capable in some ways and far more capable in others. They could forget how to build an ocean-going vessel while learning exactly how a sealed habitat ages. They might lose whole areas of medicine while becoming exceptionally good at treating the illnesses common in their own small population. Their science wouldn't stop. It would bend toward the world available to them. So the civilization that arrives may not preserve the one that launched. Its machines may be rougher and its practical knowledge narrower. Those limits would reflect generations choosing what they could still teach and make again. Arrival, then, doesn't require carrying every original capability across the dark. It requires knowing what can be surrendered without losing the power to continue. The ship survives by becoming something its descendants can still understand. A generation ship that lasts 1,000 years probably won't resemble a cruise liner with a very good repair department. It will be more like a small city cut off from every other city, then asked to stay alive through centuries of wear, accidents, births, deaths, and changing knowledge. With technology we have demonstrated, a fully closed machine packed with spares and robots doesn't seem plausible for a 1,000-year voyage. Too many parts depend on other parts. A replacement pump may require a seal, lubricant, a sensor, a calibrated tool, and someone who understands how the assembly behaves. Extra copies delay some failures, but they don't preserve the chain that makes replacement possible. The ship would need to carry part of that chain within itself. It couldn't hold every factory on Earth, or retain every branch of science. It would need enough industry to make materials, shape them accurately, test the results, and alter designs that could no longer be built. Over time, its machines would become descendants of those launched from Earth, adapted to the power, resources, and skills still available. This is a narrower and harder kind of success. The ship survives by becoming a partial industrial civilization. Its people keep deciding what they can still power and grow, what they can inspect, and what they can reproduce without help. Some systems may become simpler, because simpler versions are easier to understand and rebuild. Others may have to remain complex, because the environment allows no forgiving substitute. Education becomes part of the machinery. A manual can preserve instructions, but instructions alone don't create judgment. People need practice, teachers, working examples, and time to learn before knowledge is urgently required. A society can possess a complete archive and still lose the ability to use it. The information remains, while the living path from information to action fades, perhaps so slowly that no single generation notices the loss. The same problem reaches into the ship's biology and institutions. A farm isn't merely a food machine, and a school isn't merely storage for facts. Both depend on observation, correction, trust, and people maintaining work whose value may remain hidden for decades. The vessel's strongest redundancy may be social. Several people who can understand a system, teach it, dispute a bad assumption, and restore the skill after a disruption. None of this proves that a 1,000-year voyage is impossible. It shows why the easy version is unconvincing. We don't know how far such a society could simplify itself and still preserve the mission. We don't know how much its institutions could change before essential knowledge became ceremonial or forgotten. Nor is there a tested line showing how much ecological weakness can accumulate before recovery slips beyond reach. The uncertainty is cultural and technical at once. A ship might continue toward its destination while becoming less able to understand the systems carrying it there. It might remain inhabited while losing the industrial depth needed to repair its most demanding machines. At some unknown point, survival, continuity, and completing the mission may stop meaning the same thing, even while the engines continue running. A generation ship, then, is a society that must keep rebuilding its vessel while renewing the knowledge and cooperation that make repair possible. Its central work is preserving enough industrial, biological, and educational order for the inherited machine to remain understandable. If it reaches another star, it may not arrive as a perfectly maintained artifact from Earth. It may arrive as a changed civilization inside a changed machine, still carrying some continuity of purpose, though not in the form its builders expected. That is the most defensible hope current technology allows.